Okay, so here's the paper that I'm going to work through. October, November 2021. Let's see, paper 2. It's a total of 80 marks. I tried to pace myself according to the time here, 2 hours. I actually finished a bit quicker. And so if it's fast, you can slow it down, pause it. You can speed it up as well. So you can really go at any pace you like. So what I would recommend actually is to get the paper, try to work through it. I'll timestamp each question so that you can just go to whatever ones you need help with, or you can go through the whole thing. Okay, so without further ado, I think we can get started. All right, so for the first question, we have two absolute value functions. For part A, we need to graph them. And then for part B, we need to find the, for what x values the one function is greater than the other one. Okay. So starting in with the first function, we have y equals x, the absolute value of x minus 5. I want to get a general sense of what this looks like maybe before I start. We know that y cannot go below 0. So it's going to be a straight line, but it's going to hit the x-axis and then bounce up because it can't go below 0. And so I think it's relatively clear that when x equals 5, it's going to hit 0, and then it's going to bounce up. Okay. So that's the general picture. So we're interested in the critical value, which is the minimum. All right. So we're going to make a table. And I'm going to choose 5 because that's a critical value. And then I'm going to choose a point to the left, say 2, a point to the right, say 7. You could choose different values, but that's what I'm going to work with. Okay, so we just we stick those into the function. Start with 2. 2 minus 5 is negative 3. The absolute value is positive 3. There's our first set of coordinates. 5. We know that's 0. That's the reason we chose it. It's the place where it bounces. All right. That's the turning point. Okay, so the second set of coordinates. And then our point on the right of that is we're going to use 7. So that's 7 minus 5 is 2. Okay. Throw that in the table. And our third set of coordinates. And that's enough to draw the graph. Okay, so we go back to the number plane now. And we put these points on the graph. And we connect the dots. And there you have it. The first function. All right. Second function. Okay. Let's think about this one a little bit now. We have 6, and we're taking away the absolute value of that, 2x minus 7. Okay. So we're taking something away from 6. What's the smallest thing we could take away? The smallest thing we could take away would be 0. Otherwise, we'll be taking away more. Okay. So that means the maximum value is 6. All right. So we want to think about where that maximum value is. What x value will give that to us. So the point's indicated by the red circle. And we can see that the maximum is when the absolute value piece is 0. That will be 0 when x is 3.5. 2 times 3.5 is 7. 7 minus 7 is 0. Okay, so we go and make a table. We're going to choose 3.5. That's the turning point or the maximum point. And then we want a point to the left of that and a point to the right of that. So I'm choosing 1 and 5. Okay, so just as before, put these into the function. There's 1. That gives us, let's see, that gives us 5 inside the absolute, negative 5 inside the absolute value. And that means we take away positive 5. So we get 1. Throw that in the table. 3.5, we chose that for a special reason because we know it makes 0 inside the absolute value. And so we've got 6 minus 0 is 6. That goes into the table. And we've got our second set of coordinates. Then we chose 5 for the next one. Put that in. 2 times 5 is 10. 10 minus 7 is 3. So we have y equals 6 minus 3. All right. Zoop. Throw that in the table. And we've got 3 coordinates. And we go back to the number plane. Put these 3 points on the graph. We connect the dots. And there you have the second function. Okay. So now we want to look at them all both together. And we see that the places, or let's say the regions where the absolute value of x minus 5 is bigger than 6 minus the absolute value of 2x minus 7 is indicated by these green sections. Okay, so it's nice and clear where that function is above the other one. And so our final answers are x less than 2 or x greater than 6. We use the word or here because it could be the section to the left, x less than 2, or it could be the section to the right, x greater than 6. Okay, first one done. We're off to a good start. Okay, on to question 2. Here we have simultaneous equations, and we need to notice here that you have to give the answers in the form a plus b square root of 3. Okay, so with simultaneous equations, we need a strategy. Okay, what I'm going to do here is I'm going to eliminate the x's, and the way I'm going to do that is by multiplying the first equation by negative 2. Okay, now there are different strategies here that would work just as well, and you would develop your own strategies that you like with practice. Okay, but this one to me looks like the easiest way to go. So we multiply by negative 2, and we get negative 2x minus 2y equals negative 6. And then we can add these two equations together, and the x's will be eliminated, and remaining with the y's is negative 2 minus square root of 3. And on the right side, we have a negative 1. All right. Now we solve for y. First of all, I'm going to multiply everything by negative 1. Why do I do that? I notice that I have all negative signs here, so if I multiply by a negative 1, I can switch them all to positive. So, not that I'm against negative numbers, But if I see a nice opportunity to switch them all, then I think it makes it a bit easier. So that's what I'm doing here. So we get everything positive. Now we just solve for y. We'll divide by 2 plus the square root of 3. Okay. Now it looks like we're more or less done, but we have to remember that the form is specifically given. So we need to rationalize the denominator, okay, which basically means removing the square root from the denominator. And the tool that we use for that is called the conjugate. So in comes the conjugate. All right, the conjugate now, it looks like the denominator, except that the sign is switched. So that's what the conjugate is. Okay, instead of 2 plus square root of 3, the conjugate is 2 minus the square root of 3. And then why do we do that? Let's take a look at what the conjugate does when we multiply by it. Okay, so we're doing basically a bracket expansion here, like a FOIL method. And you notice here now that the middle terms, the purple ones, cancel. Okay, that's because of the conjugate having the opposite sign. The middle terms always cancel, and so we can eliminate the square root sign by using the conjugate. So we end up with the square roots fly away. We have a nice denominator of 1, and so there's our y. All right. Now all we need to do is solve for x. We go back to one of the original equations, and the first one is the easiest one to use. We substitute in y there, and then solving for x just means subtracting the 2 and adding the square root of 3. And final simplification, 1 plus the square root of 3. All right. I hope that you found that one relatively easy. Okay? So that's one where you should hopefully get the full marks. And now you're early in the exam and you're building confidence. So this is a nice way to start. All right. Okay, onward to number 3, where we'll do some trigonometry. The curve has equation y equals a cosine bx plus c, where a, b, and c are integers. Find the values of a, b, and c. Okay. Now we want to hopefully have some knowledge of the general shape of a cosine curve and the sine curve. That's really useful to have in your head. So what you should do probably is some practice looking at these curves. Use Desmos, I would recommend, and you can see what happens when you change the a, b, and the c. For part B, we'll have a sine curve, y equals 2 sine 3x plus 4, and then we just are going to need to write down the amplitude and the period. Okay, let's jump into it. Okay, so here's a cosine, and this is what happens when we change all the parameters at the same time, a, b, and c. Okay. Now what we need to do is look at changing one at a time, and I think the easiest one to start with is the c. C is basically a vertical shift, up or down. If it's positive, it's up. If it's negative, it's down. And we can also think of it as the midline of the function. The midline is a horizontal line, and there is as much of the function above the midline as there is below it. Okay, so that's this blue line here. Okay, with this standard cosine, it starts at 0. And then this is what happens. It goes up. There's 2. Goes down. Back to 0. And here is where we actually are with our function at c equal -1. Okay. Next, we'll look at a. What happens when we change a? So we'll keep c at -1, and then we'll change a. Okay. A is the amplitude, and it basically shows how big or how high and low it goes, the max and the mins, let's say. Okay. When it's negative, it flips down. In our example, we have the amplitude of 3. Okay, so that's the distance from the midline to the maximum. Okay, or from the midline to the minimum. Okay, that's the amplitude. Finally, we'll look at B, which is going to affect the frequency. Okay, so as B increases, the frequency is increasing. And when let's stop at 4. Okay, so 4 means that we complete 4 cycles of the cosine curve within 2 pi. Okay, 2 pi is a full circle, 360 degrees. Okay, and the B tells us how many full cycles of the cosine curve do we finish within that full circle. Okay, in this case it's 4. Okay, in our function, stretching out, coming back, our function completes 2 cycles within 2 pi. So the B is 2. And now for part B, we have a sine curve. The midline is there at y equals 4. That means C is 4. The amplitude is 2. So you just need to know what the word amplitude means and where it's found. It's the A value. And then the B is 3. And from there we can calculate the period. And the formula for the period is there. Okay. And that's it for number 3. All right, for number 4, we've got 2 log questions. They're unrelated. And indices question, also unrelated. Might want to just pause now and write those down. But I'm going to jump into it now. Okay, first thing I'm going to write down here is a basic form of the log equation. That's the first line. And then the second line is the exponential form. And so for log questions, what you want to be able to do is to be able to move from one form to the other, whatever happens to be more convenient for your particular problem. Okay, so I'm going to just keep that there. That's really like my key for any log question. Okay, now the particulars of our question. We have log base 6, 2x minus 3 equals 1/2. And I'm just going to change that to exponential form. Okay. 2x minus 3 is 6 to the power 1/2. I'm going to rewrite the power 1/2 to the square root sign, add 3 to both sides, and we divide by 2, and there's our x. All right. Now we have another log question. So we're going to use one of the rules, log rules, when we're subtracting. We can rewrite that left side as a fraction. All right. Then we're going to change it into exponential form. Okay, let's just notice here now that for the natural log, the base is e. So it's not written there, but it's implied. So the base is e, the power is 1. Now we're in exponential form. And we're just doing some basic algebra now, multiplying by u minus 4. And then we're going to multiply out that bracket and just solving this equation. We're going to factor out the u there, and then we can divide by 2 minus e, and there's u. Okay. Part B finished. On to part C, which is we're going to use the rules of indices here. All right. First thing I'm going to do is put everything in with 3 as the base. Okay. So normally these questions, you'll have like powers of 3 or powers of 2, whatever. And if I can get all the bases the same, that's going to lead to ease of solution. Okay, so we're just using powers, rules of indices. In the denominator, I multiply the 3 times 2v and times the negative 5. So that's that step. Next step is to multiply by the denominator. So we don't have fractions anymore. Now we have the same base, which means that we can equalize the indices. So if the bases are the same and we have an equation, then of course the indices also have to be the same. So now we're not dealing with the indices anymore. We're dealing with straightforward linear equation. We're going to solve for v. I'm going to do everything there in one step. Basically, I subtracted the v from the left side, giving me 5 left on the right side. And on the right side, we have a negative 13, which we add, and that's on the left now. And finally, we divide by 5. And part C is finished. Okay, on to number 5. Okay, number 5. We have a trig identity for A. And then for B, it says, hence solve the equation. Whenever you see hence, that means that you want to try to use the previous result to answer this question. Okay, let's get into it. All right, so I'm going to start by showing some of the identities that we're going to use. So we got the cosecant and the secant, tangent, and then the last 2 here, these are related. These are the sine squared plus cosine squared equals 1. And then we can write cosine squared in terms of sine squared. The first 3 are ways to write these trig functions in terms of sines and cosines. And many times it's a good idea with the identities to try to convert into sines and cosines because they're a little bit easier to work with. And especially because you can use this sine squared plus cosine squared equals 1. That's a key identity. Okay, so we'll tuck that over there in the corner, and here's our thing that we want to prove. And first thing I want to do, now by the way, there are different orders that you could do these things in. For example, you could add those fractions, get a common denominator first. What I chose to do is change everything to sines. So I'm using that first identity, and that's the result. Now, I want to simplify this a little bit, so I'm going to remove the fraction in the denominator by multiplying by sine x over sine x. Okay, there's our result. Okay, now we need to add these two fractions together, which means we need a common denominator. And the way we're going to do that is by multiplying the first fraction by 1 plus sine x over 1 plus sine x, and then the second fraction by 1 minus sine x over 1 minus sine x. Okay, there's the result of that. Now we need to expand all these brackets. There's the numerator and the denominator. Make sure you get all 4 pieces there. All right, and look at the purple pieces. You notice that these will all cancel. So this is starting to look nice, starting to simplify for us. Whenever you can throw things out, that's good. So here's what's left. All right. Now we look at the denominator, and you see the very last identity in the orange box. We can use that and substitute in cosine x, cosine squared x. Okay. Now I'm going to pull that apart into factors. And now we're going to look back at the identities and see what we can substitute in. There we have tangent and the secant. And there you have it. Left-hand side equals right-hand side. Okay, on to B, where we will use this result. So I'm going to just repeat some of the identities that we're going to use here. Tuck them away in our little orange box. Okay, here's the equation that we need to solve. So that's the result from A. So that's how we're going to write the left-hand side. Now you can see this is kind of going backwards from some of the stuff we just did. I'm writing the tangent in terms of sine, cosine, and the secant in terms of cosine. As I said, I like to work with sines and cosines. It's my preference. Okay, now we're multiplying those things together, just making it a little neater. Okay, that was a little tricky there maybe, but the multiplied, kind of a cross multiplication there, the sine x under the 5 goes up to the left side, so it becomes a square now. All right. Bringing in the tangent now for sine over cosine. So sine squared over cosine squared is tangent squared. And so tangent squared is 5 over 2. We have to take the square root of both sides. And we get plus or minus square root of 5 over 2. All right. So now, because it's plus or minus, that means we need to look at all 4 quadrants. Okay? So you really need to draw out the quadrants. Okay? And you're going to be 4 answers. Okay, so the range is from 0 to 360. So that's 1 full circle. That means 4 answers. Okay, there's actually unlimited number of answers here. That's why you have to be given a range. Okay, so let's find the first one. This is from our calculator. You'll just do the inverse tangent of square root of 5 over 2. That's what the triangle looks. You see the opposite over the adjacent, square root of 5 over square root of 2. And so there is this is called our reference angle, and we're going to basically draw that reference angle in each of the 4 quadrants. Okay, so there's the first answer, comes straight from the calculator, but the calculator can only give us 1 answer. So now we have to do the work to get the next 3. Okay. Second answer, we'll start from 57.7 and we end up there. Okay, so again, here's the triangle. This is a a negative. The tangent is negative here in the second quadrant. You see the negative square root of 2. Okay, we're basically the reference angle 57.7 short of 180. Okay, so we can get this angle by subtracting 57.7 from 180. Second answer. We proceed to the third quadrant. Same reference angle with the x-axis, you see. Similar triangle, tangent's negative, and we are 57.7 from the x-axis again, but further from 180, so we're going to add that to 180. Here's our third answer. And the final answer, we come to there, similar triangle again, and you see that we are 57.7 short of 360. So there's the last answer. All right. I think it's important to note here that when you're solving these trig equations, you have to draw the quadrants and draw the triangles there, and realize that your calculator can only give you one answer, so you have to get the rest of them. Okay, that's it for number 5. Okay, number 6, we have a couple trig functions, and then we're going to use calculus. So what I recommend is just write these down, just pause it, write them down, and then we'll get started. Okay, so I'm going to start off with some of the things that we're given. Tuck that away up in the corner. Okay, so the first is our expression for x, and then I'm going to subtract 2 from each side, so I have an expression for secant. The last line is secant squared minus 1 equals tangent squared. That's one of the formulas that's given to you. And then here's the y expression that we're going to work with. So I substituted in secant squared minus 1 for tangent squared. Why? Because that's our x is in terms of secant, right? So that's why I'm using secant there. Okay, and then for the secant, you see we have an expression for the secant. It's x minus 2, so we put that in for secant, and so now we have an expression for y in terms of x. So that's part A. Okay, part B now, we'll use that to get dy dx. So that's a fairly easy derivative to get. Use the power rule. The 4 flies away. The 2, the exponent of 2, comes out front, and that's reduced by 1. So I wrote 2 minus 1 there, but of course that's power 1, which we don't write. And so there's your final answer for B. Okay. Now C. We'll use all this stuff that we just found. So here's the given stuff, and then basically those last 2 pieces are what we found for A and B. And what we need to do here is find the equation of the tangent line at this specific point of theta equals pi over 3. Okay, so how do we find the equation of a line? We can find the equation of a line if we have the gradient and a point. So basically we have, in the gradient, we have the direction of the line, and in a point, we know where it's fixed. Okay, so that's our goal now. We need to find a point. We'll do that first. Okay, so we put in pi over 3 for theta, and there's x, and I'm gonna put that in terms of degrees. Now you should be able to work in degrees or radians, and not mind too much either way. But I'm going to use 60 degrees here because we're going to talk about this fairly famous triangle, the 30, 60, 90 triangle. So, and you could also say the pi over 6, pi over 3, pi over 2 triangle, but it's not really, doesn't have such a ring to it as 30, 60, 90. Okay, but they're the same. Okay, so the 30, 60, 90, this is a good triangle to have in your head and be able to draw it quickly because it pops up all the time in AdMath and all beyond ad math. So anytime you have a 30, 60, 90, the ratio of the sides is in with these numbers. This is in simplest terms, right? So hypotenuse of 2, the one leg of 1, the other leg of square root of 3. So any 30, 60, 90 could be scaled up or down, but the ratios will always be the same. Okay, so we're looking at the secant now, and remember the secant is the reciprocal of the cosine. So the cosine is adjacent over hypotenuse, which means the secant is hypotenuse over adjacent. Okay, so we're looking, from the perspective of 60 degrees. So put yourself up there, and then we need the hypotenuse over the adjacent, the reciprocal of the cosine. Okay, that gives us a point. That gives us the x value. Okay, so we need the y now. When x is 4, what is y? Okay, so we throw in 4, and we do the calculation. It's 2 in the parentheses, so 4 plus 4 is 8. So we have a point. Good. All right, we're halfway done, let's say. What else do we need? We need the gradient. Okay. Why do we have the derivative? The derivative gives us the gradient. Okay. So they're leading you into this, right? They're giving you what you need, basically. So we find, the gradient of the line is the value of the derivative at our specific point. So that means we put in 4 for x, and that gives us the gradient. So that's 2 times 2, which is 4. All right, we put it all together now in the equation of a line, a point gradient form. Okay, so the y1 and the x1, these are our specific points. So 4, 8, x, y, 4, 8. All right, and then just stick them in. 8 for y, 4 for the gradient, 4 for x, and basically you're done. You could leave it like this. The mark scheme, I think, leaves it in this form. I always kind of feel like I want to put it in standard form. So that's the final. I guess I wouldn't recommend, even though it looks so much nicer, the standard form. I don't know. But you don't get any extra marks for that. You might make a mistake and lose a mark. So I guess I would leave it in the non-standard form. Leave that up to you. Okay, that's all for number 6. Onward. All right, number 7, we have a vector question. You got to expect one of these. I hope with some of the visuals that I'll show you here that you'll be convinced that this type of math, although it's new, maybe for some of you, it's not too bad. You can do it. Okay, so let's take a look. Okay, so vectors. Here's a vector that's given to us. It looks like this. I'm going to call it V1. And let's just remember what the I and the J are. I is a unit vector that goes either left or right. If it's negative, it's to the left. If it's positive, it's to the right. And the J vector is a unit vector up or down. This particular vector goes to the left 5 and up 12. Okay. We're also given a vector P, and we're told that it goes in the same direction as V1. Okay. So now what we need to think about is the relationship between P and V1. Okay. And so P is equal to some scale factor times V. right? So let's just think about what the scale factor does. If the scale factor goes below 1, p gets smaller. When it's a half, p is now 1/2 of v1, pointing still in the same direction. Interestingly, a k can be negative, which means that it changes direction. It flips 180. Okay, and then here's p if k gets bigger than 1, all the way up to 2. All right, so what we need to do here is find k. If we find k, then we just multiply it by v. Okay, so we look at what we're given. We have the magnitude of p, 39. And so if we can find the magnitude of v1, then we can find k. So let's see how to do that. The magnitude of v1, if you think about the triangle that we had, those two legs, we use Pythagoras here to find the hypotenuse. All right. And these numbers are quite nice. They work out well. 169 is square root of 169 is what? It's 13. It's a good idea to know the square numbers up to 20. I would say they pop up a lot. All right. So 13 squared is 169. And from there, we can get k. So we have magnitude of p is 39, magnitude of v1, 13, and 39 divided by 13 is 3. So k equals 3. Now, all we need to do to find p is take k times v1. And multiplying a scalar times a vector is easy. You just distribute it across the parentheses. So you have 3 times negative 5, negative 15i, and then 3 times 12, 36j. Okay, so there's p for you. Okay, we're going to do that same exact thing again. You give us another vector. Here it is. They also tell us, okay, first let's look at the legs. We can think of it as a triangle. So we go 15 to the right, and we go 8 down. Okay, and then we're told that vector q goes in the same direction as v2. So again, we need to find the scale factor that we multiply by v2. Okay, so what is that scale factor? Okay, we can actually set up a little equation here for k. So k is equal to the magnitude of q divided by the magnitude of v2. We have the magnitude of q, which is 34. And so we need the magnitude of v2. We use Pythagoras. And we get the square root of 289. Maybe you know that one. What is it? 17. Okay, so they gave us nice kind numbers. K is 34 over 17, which is 2. And then we multiply that by v2 to give us q. 2 times 15, 30i. 2 times negative 8, negative 16j. And there's q. Okay, so the two problems, identical process. Part B. Part B now, we have the vector p plus q. Okay, adding vectors, no problem. When you add vectors, you add the I piece and you add the j piece. So when we add the I piece, we get a positive 15. And when we add the j piece, we get a positive 20. Okay, so there's, and we need to find the magnitude, so we use Pythagoras again. And let's just take a look at how that looks as like represented as a triangle. Okay, so we go to the right 15 and we go up 20. All right, so with Pythagoras then, we get the square root of 625. That's a pretty famous square number. What is it? 25. Okay. Now what we need to do is find theta, which is the angle that P plus Q makes with the x-axis. Okay. And now we have all the sides of this triangle. We have the hypotenuse now, 25. So you could do sine, cosine, or tangent. I'm just going to use the tangent. So that's the opposite over the adjacent. And then with your calculator, you get the inverse of the tangent, and that is 53.13. You could round that off to 53.1. Okay, so that's a vector question. I hope that you can see that that's doable. Okay, on to question 8, where we're going to use our calculus skills. This is a nice question because it shows basically the two main use cases that we've learned in AdMath for calculus. Part A, we're going to use differentiation to find the stationary point. This point's sometimes called the turning point, or could be a local minimum or maximum. And it's where the gradient of the tangent is 0. Next, part B, we're going to use integration to find the area under the curve. Okay, so on to part A. We have our function here in gold. We have a tangent line, and you can see as that moves along the curve, the gradient of the line is changing. And what we're interested in is the point where the gradient is equal to 0, or it's horizontal. Okay, this is the point where the derivative is equal to 0, because the derivative is the same as the gradient of the tangent. Okay, so we bring in our function here. I'm going to rewrite this a little bit to make it easier. We bring the denominator up to the numerator, and we have negative power of -1. And then we're going to use power rule. So the -1 goes out front. The power is reduced now to -2. 2x just becomes 2. Okay. Now we need to set the derivative to 0 and solve for x. So I'm going to move that x minus 1 back down to the denominator. It becomes positive power 2. And we go ahead and solve this. Subtract 2 from both sides. Then you multiply by the denominator. And then here I have both signs are negative. So I can switch those by multiplying by -1. And I think, why not make everything positive rather than negative? Just my preference, I guess. So that's what we've done here. So everything now is positive, and we divide now by 2. And we take the square root of both sides. And here, let me pause a little bit and explain why we can throw out the negative. Because when we take the square root, we get plus or minus square root of 5/2. But the graph that they're showing us is only dealing with positive x values. So we can throw out the negative. And to finish up here, we add 1 to both sides. And it looks like we're done. There's a our value of x. But don't stop here. We need to get into the habit of always rationalizing the denominator, okay? And it turns out, maybe on purpose, this question becomes more difficult if you don't rationalize the denominator. Maybe they put this in as a little punishment. I'm not sure, but good idea. Get into the habit. Always rationalize the denominator. What does that mean, actually? That means removing the square root sign from the denominator. Okay. So we can do that pretty easily. We bring in the square root of 2 over 2. You multiply that through, makes the denominator 2, and the numerator square root of 10. And there is our simplified version of x. Now we plug that in to y, into the function. So all those yellow bits, that's x. All right, so there's y. And we need to simplify that a bit. Okay, so the first step here, I'm basically just getting rid of the plus 1 and minus 1 and multiplying the 2 through the brackets on the right side piece. Then we have that square root of 10 over 2 in the denominator. So I can get rid of that by multiplying by the reciprocal. I'm also going to cancel those 2's in the second fraction. All right, and it's starting to look nice. Now I'm going to rationalize the denominator for 10 over square root of 10. So we do that by multiplying by square root of 10 over square root of 10. And the denominator now becomes 10. And those 10s cancel, and we have a nice simplified version of y. 2 times square root of 10 plus 2. All right. And that's it for A. We have our x and our y. All right. Onward to part B. Okay, here we have an area bounded by 3 functions. Okay, and importantly, they've given us this intersection point here of 2, 9. Okay, so we need a strategy here, and the best idea, I think, is to split this into 2 pieces. So we have area 1, area 2. Area 1 is a triangle. So that's quite easy to calculate. We'll do that one first. Since we have that point of intersection, 2, 9, we know that the base of the triangle is 2 and the height is 9. So it's 1/2 base times height, which gives us 9. So we'll tuck that away in the corner there. Now we need to get second piece. Now for this, we need to use integration because it's a curve. Okay, so the integral looks like this. Okay, we know the limits are 2 to 4 because we have that point 2, 9, and we have the line at the end, which is x equal to 4. So those are the limits of the integral. So we differentiate from 2 to 4. Okay, so I'm not going to get too deep into how we get these integrals. We have 2 different pieces here. We have 5 over x minus 1 and 2x. Okay, the first one is a natural log. So this is something that you need to know, basically. And the other one is just the opposite of the power rule. Okay, so it looks like that from 2 to 4. Now we just plug in 4 into x, and then we subtract, and then we plug in 2, and we subtract that piece with 2 in it. Okay, so the 4 goes in, we subtract, the 2 goes in here. Okay, it's worth, so we're going to just simplify basically. It's worth pausing a little bit here and look at the 5 ln 2 minus 1 piece. 2 minus 1 is 1. So we have the natural log of 1. And so what are we asking here? It's basically saying e to what power gives 1. So it's 0. E to the power 0 gives 1. So that whole thing there, 5 natural log 2 minus 1, that's 0. Okay, so we are getting more and more simplified here. We're left with 16 minus 4, which is 12. And you don't need to put that in your calculator. You can just leave it like that. Leave the natural log of 3. It's a more exact answer, by the way, because the calculator will round that. Okay, so the two pieces are there. We add them up, and you get 21 plus 5, natural log of 3. Okay, calculus, very nice. Okay, question number 9. We have an arithmetic progression, and we are given the 3rd and the 10th term. Okay, so part A, we need to find the value of A, which is the first term, and the value of D, which is the common difference. Part B, we're given a particular sum, and we need to know how many terms made that up. And then part C, we have an identity that we have to prove algebraically. Okay, part A now, start with our given information. U sub n is the nth term. That's a formula that's given to you on every exam. And S sub n is the sum of n terms. That formula is also given to you. And then U sub 3, U sub 10, those are the particulars for this problem. All right. So I'm going to write down U sub 3, U sub 10 in terms of A and D. And so we basically have simultaneous equations. So you choose your strategy here. This is my strategy. Oh, this is probably, would be everybody's strategy, I guess. We're going to subtract U sub 3 from U sub 10. Okay, so we put in the 41, which we know. Okay, when I say subtract, the way I'm writing it is I'm multiplying U sub 3 by negative 1 and then adding it, but it's just the same as subtracting. Okay, and so the result is 28 on the left side. The A's are eliminated and 7D on the right side remaining. Okay, and then we can easily get D. 28 divided by 7 is 4. Okay, so we tuck that over there with the given. That's found information. Okay, now we need to find A. We can go back to U sub 3 and solve for A. We subtract 2D. We know D and we know U sub 3, so we plug those numbers in. And we get 13 minus 8. So A is 5. Okay. Throw that over there with D, another found piece. Right, that's part A. Part B. Okay, we're going to use the sum formula there. That's given to us. So we're just applying these formulas and putting in the information that we're given. Okay, so that's the sum, 2,555. We substitute in 5 for A and 4 for D. Okay, and then we're going to just clean this up a little bit. So I've multiplied the 1/2 through the bracket. Okay, so the 2 is gone and the 4 is now a 2. further simplifying, I'm going to multiply both those brackets at the same time. Just kind of smudges in there together. So we've got 5n. The 2 is going across the n minus 1 and the n at the same time. All right. So we end up with 2n squared minus 2n. Then we'll combine all those like terms. And then subtract 2,555. It's over there. So we have a quadratic. And typically we want everything on one side and 0 on the other. And we have a couple, 2 or 3 different ways to solve a quadratic. We can try to factorize it. That number 2,555 is kind of an ugly one. I don't know what to make of it. It's not familiar to me. So when I see that, it doesn't seem so obvious that factorizing is possible or even easy. So I would just use the quadratic formula here. Okay, so then we just plug in the a, b, and the c. Okay, so that's negative b plus or minus the square root of b squared minus 4 times a times c. Okay, you notice c is negative, right? All over 2a. Okay, we'll do a little cleanup before we go to our calculator. Okay, then the key thing to notice here is that those two negatives in the square root sign become a positive. All right, and then from here, just put it in your calculator. That's the best I can say. And that's what you get. Okay. Now we do have a negative answer, but negative doesn't really make sense in a sequence, so we're going to throw that out. And we have only the positive 140 over 4, and that simplifies to 35. Okay, part B done. Yep. Now part C. All right, we have the left-hand side there. It's the sum of 2k terms minus the sum of k terms. And we want to show that it equals 3k times 1 plus 2k. Okay, so we're just going to work on the left side. And we're going to, again, use the S sub n formula. So write it out here. Both pieces. Okay. And we are going to substitute the A and the D. Okay. Both sides. The only difference in these two pieces is that one is 2k and the other one is k. All right, and then a raft full of equations on the way. Just a bunch of simplifying here. Okay. Try to follow. If it's fast, you can pause it. All right. In the brackets, we've got 10 and minus 4 there. Becomes 6. Okay, so it's slowly but surely simplifying. There, I multiply the 1/2 through the bracket to make 3 plus 2k. All right, then I'm going to multiply out the brackets because it still doesn't look exactly the way I want. Okay, you multiply that out. Then we collect like terms. End up with 6k squared plus 3k. And then now it's looking close. We take out a common factor of 3k. And that leaves 2k plus 1. And that's what we're looking for. Left-hand side equals right-hand side means you're done. Very good. That one was not too bad. You just need to apply the formulas that you're given. Alrighty, onward. All right, finally to question number 10. And if you've made it this far, good for you. Just a little more endurance to go and a few more marks to get. All right. So part A, we have a cubic, and we want to find the equation of the normal to the curve at x equals 1. Okay, so we need to know what that word normal means, and I'll give you a little refresher in a second. Part B, I must admit I don't like this question. Maybe someone can convince me that it's a good question, but I'll talk more about that after part A. Okay, so with part A, we have a cubic there. I'm not saying this is specifically our cubic. By the way, you will not have the advantage of being able to see the graph, right? So I'm using this just to show what the normal means, but you do this kind of a little blind and just using algebra. Okay, but anyway, we have a cubic function, and I've drawn the tangent at x equals 1. Okay. Now the normal is a line that is perpendicular to the tangent. Okay. So now in order to get the equation of this line, we need to know the gradient, and we need a point. And the point that we're going to go for is that point that we're pointing to, okay, which is where the tangent touches the curve. Okay, so we know x is 1, and so basically we need to find the y value. All right, so let's see how we do that. This, first of all, is the general form for the equation of a line, okay, if you have a point and the gradient. So that's what we're going to use. We already have a value for x, and so we need the y and we need the m, which is the gradient. Okay, so we go to the function, and we first get the derivative because we want to get the gradient. Okay, so we're using the power rule here. Pretty straightforward derivative. Not going to talk much about that. And then we want to find the gradient at x equals 1. So we stick in 1 for x. Okay. And a nice, easy calculation. We get 12 minus 8 minus 15, which, quick, works out to negative 11. So that is the gradient of the tangent. Okay. Now, we can find the gradient of the line perpendicular. And it is the negative reciprocal. So you switch the signs and you make the reciprocal. Okay, so we've got the gradient of the normal, 1 over 11. Okay, now we want to find the value of the function at 1. This will give us our point. So we plug in 1 to the function. Another 1 is nice because it's an easy thing to square into cube. All right, and we work that out and we get what? F of 1 is 3. All right, we have everything we need now to plug into the equation of a line formula. So we bring that over and we put in all the stuff that we've got. The y is there, the gradient is there, x was given to us, it's there, and according to the mark scheme, you can just leave it like that. Now I tend to, I said this earlier, I think, I like standard form. There's the standard form. So there's the final answer. That's the equation of the normal. All right, now talk about question B and why I don't like it. As far as I can tell, and if someone else knows of a way to do this, please put it in the comments. But with the toolbox that the AdMath student has, you're not able to do this question without trial and error. You just got to try numbers for A and see what works. Okay. Now I could be wrong. There might be a way to do it, but as far as I can tell, it is strictly you find A through trial and error. If you get lucky, then you can proceed. Now, if you've gotten this far in the exam and you have any questions that you feel are outstanding, then what I would do is spend my time on those if you've got some time left. Go back and try to get those. If you've gone through all those questions and you think like there's no problem, I got them all, then give this one a try. You're probably going to get an A star no matter what, so you're good. But I wouldn't spend much time here if you could spend it somewhere else. That's my point. Of course, when you're in the middle of it, you don't know that. So I'll explain a way we can get this with trial and error. All right, so first of all, we've got our cubic, and we're told that x plus a is a factor. So if I factorize this, I have x plus a, and then what's left is going to be a quadratic. All right. Now I know that the x times the px squared, the coefficient of that has to be 4. So in the quadratic part, I know that p is 4. Okay, likewise, 18 I know is made from a times r, so I can say a times r is 18. Okay, so we're starting to find out some things here. And then we still have to find a. So there's no way that I know except to do trial and error. So we could say, okay, we need to make 18, and so we could look at all the factors of 18, plus or minus 1, 2, 3, 6, 9, or 18. But we don't even know if r is an integer. So we actually don't even know if a is a factor. I mean, for example, a or r could be 1/2, and then a could be 36. So this is all on the assumption that r is an integer too. Okay, so anyway, you go through the trial and error. So you start with the easy numbers like 1, -1, and then you'll find that if I put in -2, it gives me 0. So that's the calculation here. And if it's 0, it means it's a factor. Okay, so we got lucky. We found the factor. All right. Now, I'm going to go back to that factorized form. Okay, and so I have x minus our factor. So x minus -2 times the quadratic. And I've put in some pieces here that we know. Okay, so we know that the coefficient in front of the x squared, this is the quadratic now, is 4. And then we also know that the constant in the quadratic must be 9. All right. We make that a positive. All right, and so there we have, we're almost there. We need q. All right, how do we find q? Well, we know that in the original function that the coefficient in front of x is -15. So how do we make that term, the x to the power 1 term? We make it with 2 times qx, and then we also make it with 9 times x. Okay, so now we have an equation. And we can set the coefficients equal, and we can solve for q. All right, not too bad. So q is -12. All right, now we have that quadratic, and we have to factorize that to find out the other roots. And as you factorize that, you'll see that it's actually a square. which means that our answer is 3 over 2. So we have two roots, -2, 3 over 2. All right. That was a race through the final question. I got to believe that there were A stars for people who didn't get this one. But if you can understand that, that would be good. All right. That is it. We are done with this paper, and good luck going forward.